Now let us look at spectral densities. Okay. There are two types of spectral densities. One is a energy spectral density, then there is a power spectral density. Depending on whether a signal of interest is an energy signal or a power signal, the total area under the spectral density curve plotted as a function of frequency is equal to total energy or average power of the signal respectively. So let us understand this. Now we have energy signal E of t. We all know that energy E is equal to minus infinity plus infinity mod g of t whole square dt. This will give us the energy of a particular signal g of t. Now when I calculate the Fourier transform of this, I will get the spectrum of energy signals. The spectrum of energy signals, if I calculate the area under the curve of a spectral curve of an energy signal, it gives me the total energy present in the signal. Similarly, I take a power signal where limit t tends to infinity 1 by 2 t integral minus t to plus t g of t mod g of t whole square dt, you will get the power of the signal. So if I take the Fourier transform of this, I will get a Fourier spectrum for this called as spectral density. Now when I calculate the spectrum area under the curve, then I will get the average power of the signal. So this is the concept of spectral densities. Now let us look at energy spectral density. So what does energy spectral density say? The total energy E is given by, as you see here, minus infinity plus infinity mod g of t whole square dt. So that will again be equal to minus infinity plus infinity mod g of f whole square df. So this is the energy under the curve. So what is that? If I calculate the area under the curve, that area will give me the total energy of the signal, whether it is in the time domain or whether it is under the frequency domain. So these two will give us the total energy. Now this is known as Rayleigh's theorem. This is a very important theorem. This is called as a Rayleigh's theorem. Now let psi g of f denote the squared amplitude of the signal and is called the energy spectral density of the signal g of t. So psi g of f is equal to g of f whole square df. Then energy is given by minus infinity plus infinity psi g of f d of f. So this psi g of f is called as the energy spectral density of the signals. Let us summarize this. Now you know what is the energy of a signal, that is given by minus infinity plus infinity mod g of t whole square dt. So when I calculate g of f, the Fourier transform of g of t, the energy will be equal to minus infinity plus infinity mod g of f whole square df. Now let us use psi g of f is equal to mod of g of f whole square. Then this psi g of f is called as the energy spectral density. Therefore, the energy can be written in terms of energy spectral density. Therefore, energy is equal to now what? Minus infinity plus infinity psi g of f df. But what is psi g of f? Psi g of f, as we all know, we have defined it as equal to mod g of f whole square. So this psi g of f is called as the energy spectral density. Now let us look at power spectral density on similar lines as we have seen energy spectral density. So what is a power spectral density? The average power of a signal g of t, whether it is a voltage or a current, dissipated in a 1 ohm load resistor is defined as P is equal to limit t tends to infinity 1 by t integral minus t by 2 to plus t by 2 g of t whole square dt. This is in fact equal to 1 by t naught square summation n is equal to minus infinity plus infinity g of n by t naught mod whole square. So this is known as a Parseval's power theorem. So what is it we have done here? We are trying to find out what is the average power of a signal. The signal can be either a current signal or a voltage signal, etc. So what is the current flowing in a 1 ohm resistor? What is the voltage drop across a 1 ohm resistor? That we are trying to find out what is the power, average power. That average power is given by P is equal to a limit t tends to infinity 1 by t integral minus t by 2 to plus t by 2 mod g of t whole square dt. This is what is the power. This is called as a Parseval's power theorem. So when I talk in terms of the frequency domain, this can be written as 1 by t naught square summation n is equal to minus infinity plus infinity mod of g of n by t naught whole square. So when I sum this all these components, I will get the average power of the signals. So this is called as a Parseval's power theorem. Now let us see. Let SGP of f define the power spectral density of a periodic signal Gp of t as that function of frequency, the total area under which yields the average power of the signal. So let us take a power signal which is periodic, then P will be equal to minus infinity plus infinity SGP of f df. okay, where SGP of is defined as 1 by T naught square summation n is equal to minus plus infinity mod of G of n by T naught whole square. So, this is called as the SGP is called as the power spectral density. Let SGP of f define the power spectral density of a periodic signal Gp of t as that function of frequency, the total area under which yields the average power of the signal. P is equal to minus into plus infinity SGP of f df, that is equal to 1 by T naught square. SGP of f is equal to 1 by T naught square summation of minus into plus infinity G of n by T naught whole square delta of f minus n by T naught. Now, let us look at what is called as a autocorrelation function. Autocorrelation function actually is a measure of similarity between two same signals. One signal, let us say G of t, and its shifted signal G of t minus t1 or t2, something like that. So, what is the similarity between these two functions when they are compared? One is compared with a shifted function of the same signal. So, what is the similarity that exists between these two signals? That gives us what is called as a autocorrelation. Let us define what is autocorrelation. So, what is autocorrelation? Autocorrelation process provides a measure of similarity between a signal and a replica of the signal delayed by a variable amount and is a function of the delayed variable. That means there is a function g of t and there is the same function g of t delayed by a certain variable tau, let us say. So, g of t minus tau. So, autocorrelation function is defined with respect to the delayed variable that is equal to tau. Let us see the formula. Now, again there are two types of signals as we have seen. You have energy signal, you have a power signal. Both are different types, we know. So, we have to calculate what is the autocorrelation function of energy signal separately. We also should calculate what is the autocorrelation function of a power signal. Let us start off by finding out what is the autocorrelation function of an energy signal first. Okay. So, let us see this. The autocorrelation function of energy signal is obtained by integrating the product g of t and a delayed version of its complex conjugate, that is Rg of tau. What is Rg of tau? We are saying that autocorrelation function must be in terms of the delayed variable. So, what is the delayed variable here for us? Tau. So, Rg of tau, that's the basic definition which you have defined. We said earlier that autocorrelation function gives us a similarity between a function and its delayed version, delayed by a certain variable. So, the autocorrelation function is defined in terms of the delayed variable. So, what is the delayed variable here? For us, the delayed variable here is tau. So, let us just define this Rg of tau here. So, Rg of tau is defined as integration of minus infinity plus infinity g of t multiplied by g star of t minus tau dt, that is a complex conjugate star of t minus tau. So, the delayed variable tau is also how the autocorrelation function is defined. So, Rg of tau is equal to minus infinity plus infinity g of t g star of t minus tau dt. So, here the parameter tau is called the scanning or the searching parameter. So, as tau is varied, the value of the autocorrelation function also varies. As tau is varied, the autocorrelation function of the energy signal also varies. Now, let us look at the properties of autocorrelation function of energy signals. The first property is follows. Property 1 says the autocorrelation function exhibits conjugate symmetry, that is Rg of tau will be equal to its complex conjugate Rg star of minus tau. Here the real part is an even function of tau, whereas the imaginary part is an odd function of tau. So, property 1 says that the autocorrelation function exhibits conjugate symmetry, that is Rg of tau is equal to Rg star of minus tau. The real part of the function tau is an even function, whereas the imaginary part is an odd function of tau. So, let us see the second property. The value of the autocorrelation function at the origin is equal to the energy of the signal, that is Rg of 0 is equal to minus infinity plus infinity mod g of t whole square dt. This is nothing but the energy of the signal. That means, when I take the value of the autocorrelation function at tau is equal to 0, this gives me the energy of the signal. Let us see the third property. The third property says the maximum value of the autocorrelation function Rg of tau occurs at the origin. So, it says the maximum value of the function Rg of tau only occurs at origin. That means the similarity is maximum at t is equal to 0. That is obvious. Let us see this. Let us say this is the function, okay, and at origin what happens? This is again the function, there is no delay. So, both the functions are existing at the same place. That means the delayed version of the signal and the actual signal which is not delayed, that is tau is equal to 0. The energy will be, of course, the value will be maximum here, because the maximum means what here? Maximum similarity. Okay. Afterwards what happens? They change. When they change, the similarity tries to reduce. So, the value of Rg of tau at 0 will be the maximum value. Any value that is different from this value will always be less than the value at Rg of tau, that is at equal to 0. The autocorrelation function will have a maximum value at the origin. When I say a maximum value, means it will have the maximum similarity between the signal and its delayed version. So, Rg of 0, that is tau is equal to 0, will have the maximum value. Let us see the property 4. The autocorrelation function Rg of 2 and the energy spectral density form a Fourier transform pair. That is, the autocorrelation function Rg of tau will have a Fourier transform pair in the form of the energy power spectral density. The autocorrelation function Rg of 2 and the energy spectral density form a Fourier transform pair. These two form a Fourier transform pair. Now, let us look at the autocorrelation function of power signals. Okay, as we all know, power signals generally are periodic signals. So, if I calculate the periodic signal autocorrelation function, that is as well as application to a power signal. So, let us look at this now. What is autocorrelation function of power signal? G of t is given by Rg of tau limit t tends to infinity 1 by t minus t to plus t g of t g star of t minus tau d tau. Here our Gp of tau indicates that this is a periodic signal, that will be equal to 1 by t naught integral minus t0 by 2 to plus t0 by 2 Gp of t Gp star of t minus tau d tau. Now, this is the autocorrelation function of a periodic signal. So, let us see its properties. What are the different properties of a autocorrelation function of a power signal? So, let us start off with the first property, property 1. The property 1 says the autocorrelation function of a periodic signal or a power signal exhibits conjugate symmetry, that is Rgp of tau will be equal to Rgp star of minus tau. Here Gp indicates it is a periodic signal. Okay, this property is similar to the property of a autocorrelation function for energy signals also. Let us see the second property. What does the second property say? The value of the autocorrelation function at the origin is equal to average power of the signal. That means Rgp of 0 will be equal to 1 by t0 minus t0 by 2 to plus t0 by 2 Gp of t whole square dt. That means the autocorrelation function at the origin for an energy signal is equal to the energy of that signal. When I calculate Rgp of tau at tau is equal to 0, this will give me the average power of the signal. So, Rg of 0 will give me the energy of the signal for energy signals, and Rgp of 0 will give me the average power of the signals for a power signal. This is the property 2 of autocorrelation functions for periodic signals. Let us see property 3. So, what does property 3 say? The maximum value of the autocorrelation functions at the origin. This is similar to the property number 3 of autocorrelation functions of energy signal. We have seen that the maximum value of autocorrelation function can occur only at the origin, because this is where the tau is 0. So, this intuitively we can say that the maximum value, the value will be maximum at this place because there is no time delay. The same thing here, a power signal you take, the power signal also will have a maximum value. The autocorrelation function I take for a power signal is also will have a maximum value at origin. Then let us look at the property number 4. What does property number 4 say? The autocorrelation function and the power spectral density form a Fourier transform pair. That is, RGP of tau will have a Fourier transform SGP of f. That means, if I know the autocorrelation function of a power signal or a periodic signal, that will be equal to the power spectral density SGP of f. So, both these form a Fourier transform pair. The autocorrelation function is periodic with the same period as the periodic signal itself. That is, RGP of tau will be equal to RGP of tau plus or minus NT naught, when it can be 1, 2, 3. So, the repetition of the autocorrelation function is same, or the periodicity of the autocorrelation function is same as the period itself. That is what the other part. Now, let us look at what is called as a cross correlation function. So, as is obvious, autocorrelation function is where we are trying to find out similarity between the same signal and its delayed version. Cross correlation actually talks about the similarity that exists between two different signals. So, let us see what is the definition. The cross correlation function measures the similarity between the signal and the time delayed version of a second signal. So, when I talk about a cross correlation, I am talking about two signals. Let us say signal 1 and signal 2. So, when I want to know what is the similarity between the signal 1 and the delayed version of the signal 2, that gives me a cross correlation. What was autocorrelation we have seen? We have taken the same function 1 and we are trying to find out the similarity between that function itself and its delayed version of the same signal. Whereas cross correlation talks about two different signals. So, let us see that. The cross correlation function measures the similarity between a signal and the time delayed version of a second signal. As we have seen, the cross correlation again has to depend on the type of the signal, that is, whether it is an energy signal or a power signal. Okay, let us first look at cross correlation of energy signals. Let us take two signals, G1 of t and G2 of t. These are the two different signals. Now, the cross correlation talks about the relationship between G1 and G2, which is delayed. So, G1 and G2, which is delayed. So, what is G1? Let us see what is the cross correlation here. The cross correlation of G1 of t and G2 of t signals is defined by R1 of 2 tau is equal to minus infinity plus infinity integration G1 of t G2 star of t minus tau dt. Okay. So, here R1 of 2 means R1, that is G1 is not delayed, whereas R2, that is the second point, 2 is delayed. That means R1 of t of tau is equal to minus infinity plus infinity integral G1 of t into G2 star of t minus tau dt. So, that is how you calculate the cross correlation function. Now, the two energy signals said to be orthogonal over the entire time interval if R12 of 0 is 0. That is, the cross correlation function is 0 at 0, that is t is equal to 0 or tau is equal to 0, then they are said to be orthogonal. That means minus infinity plus infinity integral G1 of t G2 star of t dt is equal to 0. Now, when I can have R12, I can also have R21 of tau, isn't it? So, let us see what is R21. R21 of tau is equal to minus infinity plus infinity G2 of t G1 of star of t minus tau dt. R12 of tau is equal to R star of 21 of minus tau. And generally, R12 of tau is not equal to R21 of tau. Okay. Then, what is R12 of tau? Fourier transform, that is equal to G1 of f into G2 star of f. This is called as a correlation theorem. So, correlation theorem states that R12 of tau is having a Fourier transform of G1 of f product of G1 of f and G2 star of f. This is called as a correlation theorem. Similarly, we can look at cross correlation of power signals. The cross correlation of a power signal is given by R12 of tau is equal to limit t tends to infinity 1 by t integral minus t to plus t G1 of t G2 of t minus tau dt. the signals are orthogonal if limit t tends to infinity 1 by t integral minus t to plus t g1 of t g2 star of t minus tau dt is equal to 0. This is when they are orthogonal.